The trace of a matrix, this is an important notion for us. The trace of a matrix is the sum of the diagonal elements. And the unique feature is that the trace of A times B is going to be the same as the trace of B times A. So the order in which we do the multiplication doesn't matter. And it's easy enough to demonstrate why it doesn't matter by writing out the result of A times B symbolically. And so A times B symbolically is that matrix of four sums. When you add up the diagonals, you add those two terms together. B times A was a 3 by 3 matrix composed of those 9 sums. The trace is the sum of the terms on the diagonal. So you're adding up those 3 terms. And when you do a little bit of algebra, you can show that those are two equivalent forms. So the trace of A times B is the same as the trace of B times A, and that will turn out to be important to us later on when we're proving some things about out of distributions and proving some things about properties of estimators. Because sometimes the first way we write things down is a little bit awkward in figuring out the trace, so you can change the order of things. Sometimes you can cancel some terms, and then it's easy to see what the trace is. So that's a little statement, it's a little theorem that we have to remember for later on. What happened to the question?
When you're talking about the diagonal elements, are you always going from the top left to the bottom right? You never go from the top right to the bottom left? Okay.
No. So, the diagonal there's a matrix of some order. The diagonal is those set of entries for which the row index and the column index are the same. When we're addressing a term, a single element of the matrix, the row index always comes first and the column index always comes second. That's just a convention. So the main diagonal are those terms for which the row column indices are the same. Sometimes we'll talk about the off diagonals. And when you talk about the off diagonals, in this instance, the row index everywhere on that first lower off diagonal, the row index is going to be one greater than the column index, all the way down. And the reverse is true when we're looking at the upper first off diagonal. And sometimes, I can't remember exactly where it comes up, but sometimes we worry about what's on the off diagonals.
Math cat that we're looking at here?
This is math cat, yeah. I remember where the problem for the positive do that. I think my website has on it about, I don't know how many, close to 10,000 pages. It's like having 5 or 6 filing cabinets full of stuff. But at this point, most of it's unlabeled. Okay, so let's try to figure out what I have in mind. Let's talk about the determinant of a matrix. Some of you, how many of you have had matrix algebra before? Yeah, almost everybody. Anybody who has not? No harm, no foul. Matrix algebra is just a little souped-up version of scalar algebra. There's nothing special about it. You just got to keep track of a couple of more things. There are a few operations in matrix algebra which don't exist in scalar algebra. One of those is, well, the trace of a number is the number, because it's a matrix with one entry in it. And so the trace of a scalar is just a scalar. And actually, we're going to exploit that property. I forget exactly where it happens, but it is something that's going to come up later. We take the trace of a scalar, just because it's an operation that ends up not doing anything. The determinant of a scalar is, again, it just returns the scalar. In matrix algebra, what's the geometric interpretation of determinants? Is that here? Hillary. Hillary Lynn. You know what the geometric interpretation of the determinant is? Right. What's the inverse of the number 2? Just so that everybody knows what we're talking about. What's the inverse of the number 2? The inverse. A half. Right. Well, it would be nice if in matrix algebra we had the same kind of concept. If we had a matrix A, and we could figure out its inverse, then the original matrix times its inverse ought to give us something that's equivalent to the number 1. It's just like when you take the number 2 and multiply it by its inverse to get back to number 1. And so in matrix algebra, when you have a matrix A and you multiply it by its inverse, either pre-multiply or post-multiply, you get back an identity matrix. It's a matrix that has 1s on the main diagonal and 0s everywhere else. That's the matrix equivalent of the number 1. So now to come back to the determinant of the matrix. We're still looking for the geometric interpretation of a determinant. Yeah. The area of the shape enclosed by the vectors that make up the matrix. When you were in, as I mentioned, I have one child that's 26. He's a finished product. He's an electrical engineer. He's been working now, I guess, for 3 years. He's got 3 patents. He's got 10 people that work for him. So he's a pretty talented kid. I have a daughter that's 14. She's in 9th grade. And so at this point, I know what happens more or less in math classes through the grades. And so, for example, although she doesn't know that she's doing it, she has been computing the determinants of matrices already. She started doing it in that 7th grade, although they didn't tell her that that was what she was doing. Otherwise, I'm sure she'd be very upset. What they've been doing now is they've been given parallelograms in a 2-dimensional plane. And their teacher has been giving them the coordinates, teachers, of the 4 points. The origin is one of them, and then the other 3. And then they have to figure out the area of the parallelogram in the plane. And I'm sure that when you had Miss Crabtree for 9th grade math, you did the same thing. You did those kind of problems over and over and over again until you were really sick and tired of them. And the other thing you did in 9th grade was, if John has X pounds of nuts that cost $3.20 and Y pounds of nuts that cost $4.95, and he's got a total of 20 pounds, how many pounds of X did he have and how many pounds of Y? Doing those things too. So you guys have all done this stuff before.